All right, Spartan fans, section 9.1, polar coordinates. As you can see, I have a very pretty graph on my paper. These are all on Google Classroom. There's a sheet of them, so I highly recommend that you, use these, cut them out, tape them in your homework, or glue them or whatever. But using polar coordinate graphs are going to be pretty important for your success in this chapter. Okay, well, you know how to graph in a rectangular coordinate system. Let's learn how to graph in a polar coordinate system. For this particular graph, and every one that you find on the internet might be a little bit different, each one of these little diagonal lines represents a degree measure. So 10 degrees, 20 degrees, 30 degrees, etc. And I'm not going to label them all. I'm just going to label like 30, 60, 90. So 30, 40, 50, 60. And we will do radians as well. So for example, this point right here would be 210. So these are going in increments of 10 degrees. Each circle represents a radius of 1. Each circle represents a radius of 1. So what does this look like? If I asked you to plot the point, let's say 3, 210 degrees. What used to be X is now R, and that is the radius. And what used to be Y is now theta, and that is your angle measure, which I'm sure goes without saying. So if I ask you to plot the point 3, 210 degrees, even though the radius comes first, I can't stress to you enough that you should find the angle measure and then the radius. So 210 degrees is on this diagonal line right here. And 3 means I would go 3 circles, so to speak, from the origin. So the first circle, the second circle, the third circle, and I'll just call that point A so that we can use more than one. I don't want to have to cut and paste a grid for every single point that we do. So let's try and maximize our graphs. If I ask you to plot the point, we'll just call it point B. And let's say that is the point, how about 2, about negative 45 degrees. So I have to approximate where negative 45 is because I'm going by, my intervals are 10 degrees and 45 degrees is somewhere in between. So this is going to be 10, 20, this is negative 30. Keep in mind, negative 30, just a little side note, negative 30 is the same as positive 330. Don't forget that. They're coterminal. This is going to become super important in a minute. So negative 45 is like here-ish. And then 2 radii, 1, 2, it would be about there-ish. Let's do one more. Let's say, let's do a negative radius, actually. Okay, let's do point C. How about negative 4, and let's do 240. This is going to be interesting. How do you graph a negative radius? Well, you can graph like on a coordinate plane. If you have an XY coordinate, Cartesian plane, sorry, that's its technical name, it's a Cartesian plane. You can plot negatives, right? Negative 2, 1. Okay, negative 2, 1 is here somewhere. So you can plot negatives on a Cartesian coordinate system. Well, you can also plot negatives on a polar coordinate system. Find the 240 first. So 240, 20, 30, 240 is here. The previous two problems, I said, find the angle measure. So we found 210. And I said, okay, we're going to go 3 radii, 3 circles towards 210. I went 1, 2, 3, and we plotted the point. And then for 2, negative 45, I said, okay, let's find negative 45, which was here. And then from the origin, we went 1, 2 circles toward the negative 45 degree angle. Well, now instead of going from the origin toward the angle, I'm going to go from the origin away from the angle. So I'm going to find 240, which is right here. It's going to dot it in. So here's 240. And I'm going to move 4 radii, 4 circles, 4 radii away from 240. So if I were to keep extending this, (240), 4 circles, 4 radii, a length of 4 radii in the opposite direction would be 1, 2, 3, 4, and that would be right here. Well, this leads to an interesting concept because point C, I can get to point C several different ways. If you look, I have that labeled as 60. Well, isn't that the same thing as positive 60, positive 4? If I find 60 degrees and I move 4 in the same direction, these are the exact same point. That doesn't happen on the Cartesian system. But you know what? There are a lot of ways. Well, there's an infinite number of ways, but there are 4 unique ways to get to point C. We go back to the fact that negative 30 and positive 330 are the same angle. Well, guess what? Positive 240 is the same as negative 120. That's a plus sign. So I could say that point C is the same as negative 4, negative 120. Find the angle. Negative 120 ends up being at the same place as positive 240. Start at the on the x-axis. Negative 120 takes through the same place as 240. So if I find negative 120, which is on this ray, and I go 4 radii in the opposite direction, same place. And 60 degrees, positive 60 is the same as negative 300. Positive 60 is the same as negative 300. So if I said positive 4, and what did I just say? Negative 300. Negative 300 degrees takes me up to positive 60 degrees. And then I move 4 radii, I end up at the same point. So now every point on the polar system can be written with positive radius, positive theta, positive radius, negative theta, negative radius, positive theta, and negative radius, negative theta. That doesn't happen. Oh, and then don't forget, you can keep adding 2 pi, plus 2 pi k, plus 2 pi k minus. So for this one would be plus 2 pi k. This would be minus 2 pi k. So there are a lot of ways to write the measure of an ordered pair for polar coordinates. Let's get another graph and practice some more. Voila. All right. So let's start with the positive. Let's look at 3 and how about 120? So there's a reason why I told you should find the angle measure first. And what I'm going to do is I'm actually going to draw it in both the positive and negative radii. So 120 is 90, 100 here. This might be helpful for some of you. The positive angle and the positive radius are in quadrant 2. Find 120, move 3 from the origin toward positive 120, 1, 2. That's right here. $120. How else can you get to 120? You can get to 120 going the opposite direction, negative 240. Pretty sure that you'll agree with me on that one. So if I use a positive radius, 3, the corresponding negative coterminal angle is negative 240. Okay. The positive radius takes me to quadrant 2. A negative radius is going to take me away from quadrant 2, which ends up being in quadrant 4. So I need a quadrant 4 angle with a negative radius. Quadrant 4 angle, negative radius, go the opposite direction, will end up in quadrant 2. So I know that I'm going to have negative 3 with a positive and negative 3 with a negative. Those are your options. Positive radius, positive negative angle, negative radius, positive and negative angle. Okay, so to get an angle in the 4th quadrant, so how do I get to this angle right here? And I believe that angle right there is negative 60 degrees. So if I have negative 60 degrees, if I find negative 60 degrees, which is in the 4th quadrant, and the negative radius says, instead of going toward the 4th quadrant, move away from it, I'm going to end up at the same location as 3, 120. How do I get to this 4th quadrant angle? By going in the positive direction. Well, negative 60 is the same as positive 300. And there you go. Those are 4 ways to get to the same location. I can convert all of these polar coordinates into a rectangular system. So let's take a look at that. Let's say you are given the point negative 2, 2 pi over 3. Negative 2, 2 pi over 3. Okay, so if we were to graph this on our polar graph, grab one. Isn't it amazing how it just magically appears on the video? So negative 2, 2 pi over 3. Okay, so 2 pi over 3 is in the 2nd quadrant. So negative 2, 2 pi over 3 is in the 4th quadrant. So 2 pi over 3 is 120. Whatever, oops, sorry. It's up here somewhere, 120. Right there. And then negative 2 means I'm going to end up in the 4th quadrant. So I believe it's right there. Okay. If I were to superimpose a regular Cartesian plane on top of my polar graph, right, you would have, you would have this really bad but you would have, you know, the X, Y, the coordinate grid, etc. So -2, 2 pi over 3 does pertain to, does mirror a point on the Cartesian system. So how am I going to figure out what that is? Okay, so if I were to draw my triangle, which we have been doing forever, X represents the cosine, Y represents the sine, but we've always done that with a radius of 1. So X has always been cosine and Y has always been sine, but we've always done it with a radius of 1. Well, in this case, the radius is 2. The radius is not negative. The negative tells you what direction you're going. So the it's like a side length is never negative. It just happens like when we draw our triangles. Sorry, I'm all over the place. When we draw our triangle and we say, okay, whatever this is, make, you know, negative root 2 over 2, root 2 over 2. The actual length of the side is not negative. It tells you its location on the unit circle. So this is the same deal. The radius is positive 2. So how do I figure out what -2, 2 pi over 3 is on a Cartesian system? Well, you've got X is cosine, Y is sine, but like I said, the radius isn't necessarily 1 anymore. So it's going to be whatever radius is times the cosine, and Y equals the radius times the sine. So this is how you are going to convert a polar point to a regular Cartesian point, you know, with an XY axis. So for -2, 2 pi over 3, X is going to be -2 times the cosine of, what's the angle? 2 pi over 3. And Y is going to be -2 times the sine of 2 pi over 3. And when I'm done, my point better be in the fourth quadrant because that's where -2, 2 pi over 3 lies. So this better lie in the fourth quadrant. So the cosine of 2 pi over 3, -1/2. So the X coordinate is going to be 1. That's good. It better be 1, or positive at least. And the sine is positive root 3 over 2. That is negative root 3. So 1 negative root 3 on the rectangular system is the equivalent of -2, 2 pi over 3 in the polar system. 1 negative root 3, sure. I am sure there are probably several apps, you know, something online that will show you the image of the two of them together. Probably be helpful. Okay. Well, now we got to go the other way. So now what happens if I give you a rectangular point? I'm not going to review how to plot points. I think you know how to do that. What happens when I give you a point and you're asked to convert it to the polar system? Well, remember, there are 4 different ways that you can write a polar point. So it can kind of get a little bit gnarly, but not horrible. Let's say we have -2, -2 root 3. Okay, so if I was to plot this on a regular Cartesian plane, -2, whatever, -2, -2 root 3 is down here somewhere. Okay, so it's we're in quadrant 3. So when I'm done and I transform this to polar, my answer better be in the 3rd quadrant. Well, you know what? This is actually not nearly as bad as it looks. -2, -2 root 3. What I need to know is theta and the radius. So I need to find theta and the radius. You know what? You already know how to do both of these things. How do you find the radius? That's right, Pythagorean theorem. -2 squared plus -2 root 3 squared equals r squared. So that is 4 plus 4 times 3 is 12. R is 4. R is 4. All right. Well, how am I going to find out the measure of theta? Well, this goes back to your SOHCAHTOA days. Theta, how about, I know the opposite, I know the adjacent, I believe that is tangent. So how about the tangent of theta is -2 root 3 over -2, which is the square root of 3. Okay. Let's see, who has a tangent of root 3? I believe that is 60 degrees. Yeah, I think so, 60 degrees. So 60 degrees in quadrant 3. How much is 60 degrees in quadrant 3? 4 pi over 3. So this point would be 4 pi over 3. Okay, so let's do a summary. Let's do a summary. You're going to go from polar to rectangular. X is r times the cosine, and y is r times the sine. And if you're going to go from rectangular to polar, if it's rectangular, you know x and y, you need to find r. If it's rectangular, you know x and y, you need to find theta. Let's do another rectangular to polar where you're going to trip yourself up, but it's not nearly as, you're going to make it harder than it is. So let's say you have the point 0, 2. Okay, so this is rectangular, and I want you to convert it to polar. It's on an axis. 0, 2 is right here. What's the angle measure? 90 degrees or pi over 2. We're gonna go back and forth. I'm gonna try to stick to radians just because the more you do it, the easier it is. And what's the radius? 2. That's it. That's it. Let's move on to some equations. Let's move on to some equations. I'm going to give you an equation in rectangular form. Something like, you know it's in rectangular form because it has x's and y's. And I want to convert this to polar. Okay. Ooh, I don't know. Sure you do. Let's do some substituting. Let's do some substituting. we know that x squared plus y squared is r squared. We know that x is r cosine theta. So I just did a straight substitution there. I just did a straight substitution. X is r cosine, and x squared plus y squared is r squared. So the hardest part for these equations is going to be, when do I stop? How much substituting am I supposed to do? How much factoring and reducing am I supposed to do, etc. Okay, so your book does something very bad in Miss Babiak's standards. Your book divides by R and says that this is what they do, and you should be thinking right away, ooh, that's bad, and I know why that's bad. Why is it bad? Think about it. That's right, it's an equation. You just changed the degree and you've eliminated solutions. So your book will write it as r equals cosine theta. Going back, I would subtract r from both sides, make it equal to 0, and I would stop there. This is going to take a lot of getting used to. That's it. You have just converted this rectangular equation to a polar equation. Okay, let's do it the other way around. Let's take a polar and convert it to a rectangular. We'll start with something not so bad. Okay, so this is polar. It has an R in it. It has to be polar. Think about that. The radius is 4. This is the equivalent of a line. No, I mean, I'm sorry, this is not a line, but it's the equivalent in rectangular form. When you have x equals 4, it's a vertical line. Doesn't matter what y is, all the x values are 4. Or if I gave you y equals 4, it's a horizontal line. Doesn't matter what x is, all of the y values are 4. So in this case, who cares what theta is? Doesn't matter what theta is. Here, let me find another graph. These aren't really circular now that I look at them. They're kind of ovular. Anyway, sorry. So if r is 4, 1, 2, 3, 4, I don't care what theta is, r is 4. For every value of theta, r is 4. But what does that look like? It's a circle with radius 4. That's what this is. So if r is 4, r squared is 16. X squared plus y squared equals 16. That is a circle with radius 4. Let's do one more from rectangular, polar to rectangular, a little bit more involved. Okay, let's look at r is equal to sine minus cosine. Okay, so it's definitely in polar because it's got all the r's and the thetas in it. And I want to convert it to rectangular. So there is no substitution for r. I mean, I could say that r is the square root of x squared plus y squared, but I'm not sure that's going to help me. There's no flat out substitution. There's no substitution for sine or cosine, but, if I take this entire equation and I multiply it by r, that's allowed. We don't like to divide by variables. Multiplying is no problem. This is going to give me r squared equals r sine minus r cosine. I like this. I like this. R squared, x squared plus y squared. Cool. R sine, y. R cosine, x. This is doable. So r squared is x squared plus y squared. R sine is y. R cosine is x. I hate to tell you this, but you do know how to do this. I'm silent on purpose. Add x, leave room to complete the square. Subtract y, leave room to complete the square. Complete the square. Let's see. Coefficient is 1. Half of 1 is a half, squared is a fourth. And then again, y squared minus y. Half of the coefficient is 1/2, squared is 1/4. And then you have to add that to both sides. Factor x plus 1/2 quantity squared plus y minus 1/2 quantity squared equals 1/2. This is a circle. Center is at negative 1/2, 1/2. And the radius is square root of 1/2, which is root 2/2. Okay, that's it for the lesson. If you would like to stop here, but I am going to show you a little bit on the calculator so we can see what some of these things look like. So here we go. Oh, I was doing some other things. I was checking the answer to the quiz. Okay. Change your mode. And now we are going to go down to function. You should be in radians, by the way. Let's change that to radians. I was in degrees. And polar. This is going to be so awesome. Not sure if you've ever wondered, but you know the X key that says X, T, theta, N. Now when you go to your Y equals, look at that. They all say R instead of saying Y. And when you push the X, T, theta, N key, X doesn't show up anymore. Now theta does. It's pretty cool. Let's just look at that last one. Oh, you know, let's just do 4. Let's do R equals 4. That was here, was a circle. X squared plus y squared equals 16 in rectangular form. It's given to us as polar form. And when you graph this, there it is, circle. Totally cool. Circle with radius 4. Let's look at the last one that we just did. It was R equals sine minus cosine. Make sure you're in radians. So sine theta, close your parentheses, minus cosine theta. Is that what it was? Yeah. Look how small that circle is. Let's look how small that circle is. I'm going to change my window. Let's see here. I'll go from 0 to 10. And oh, I totally messed that one up. How about negative 10 to 10? That would have been better. And my y doesn't need to be so big. So it looks ovular, but that's because my windows, I'm sorry, I didn't even realize that it was messed up. Sorry. Let's change our x min to -2, +2, and now this should show up. There we go. I changed my x to go from -2 to 2 and my y to go from -2 to 2. And there it is. It's a circle. The center of this circle is somewhere in quadrant 2. Center of this circle is somewhere in quadrant 2, and negative 1/2 is definitely in quadrant 2. So we're going to learn how to graph some totally cool things. You might want to, take time to plug in some funky things. Sine squared. Let's just do a cool one, like 5 times the sine of 2 theta. Oh, that's because my window's messed up. There we go. Learn how to make petals and all kinds of cool things. That was 5 sine of 2 theta. So you are going to learn how to graph these, by the way. They're pretty fun. Okay, that is it for section 9.1.